Okay, so consider this family of differential equations. dy dt is y squared minus 4y plus mu. So the derivative is this quadratic. I've graphed the derivative function. Our goal is to see what the solutions to this differential equation look like and how they depend on mu. So we're going to begin by investigating parabolas that look like y squared minus 4y plus mu. So I'm using f sub mu. So that's going to indicate the value of mu I'm considering for this particular example. So right now I'm going to consider a value of 0, f sub 0 of y. So that just means replace the mu with a 0, so you get y squared minus 4y. And I graphed it here. Okay, so we got a parabola graphed. And then on yours, does it say draw phase line? Yes, it's draw phase line for dy dt equals y squared minus 4y. Right? That's f0. Okay, so a phase line based on this graph, where are my equilibrium points going to be? 0 and 4. Okay, and when I'm less than 0, positive or negative? Less than 0, this is the graph of the derivative, it's positive, right? Which means that the function is going to be increasing. Between 0 and 4, the derivative is negative, which means I put a down arrow. And greater than 4, the graph of the derivative is positive, up arrow. So there's my phase line. All right, if I were going to graph parabolas for other values of mu, not just 0, how would they relate to this graph that I just drew? Move up and down, shift up and down. By mu, right? Whatever mu is, that's how much it moves. Okay, so for finding a bifurcation value. So a bifurcation value is when you have a qualitative change in the solutions to a differential equation. So currently, according to the phase line, there are 2 equilibrium points. What mu value, or what would that graph have to look like in order to have only 1 equilibrium point? Yeah, I'd have to move that graph up 4 units so that it would just touch the x-axis once, right? Because those x-intercepts are equilibrium points. And so if to go from having 2 to having 1 would happen when the vertex of the parabola was right on the x-axis. All right, so trying to draw that parabola, something like this, I don't know. Not being too careful on that one. Now I want to find the value of mu that will give that parabola. Okay, so these are typos. On your sheet, it should say f sub mu, not f sub 0. Yeah, tell me the answer. What value of mu? Yes, great. So that's how we can find it. Like in this case, it's pretty easy to just look at the 2 graphs and say, oh, we moved it up 4 units, mu has to be 4. But in more complicated situations, the way that you find the bifurcation value is that your function, f sub mu of y, has to equal f sub mu prime of y. Both have to be 0, right? In order for this to be tangent to the x-axis, the derivative has to be 0 there, right? So that you have the minimum occurring, and the function value has to be 0 there, right? So that it's sitting right on the x-axis. So those 2 things will help you find the bifurcation value. So let's go through it, even though we know what mu is just by looking. The one you're going to do in your activities is a little harder, so we'll just go through the formal process. So start with the derivative, because the derivative function is often a simpler looking function than the function itself, especially if it's just some kind of polynomial. So f sub mu of y was y squared minus 4y plus mu from up here, y squared minus 4y plus mu. Okay, so let's look at the derivative. Oops. F sub mu prime of y. What's the derivative of this thing? 2y minus 4. Yep. We set that equal to 0, and you get y equals 2. Take whatever you get here, y has to be 2. That's telling you the x location, or well, the y location, right? The x coordinate, or the, it's technically the y coordinate, of the vertex, right? The horizontal coordinate of the vertex. And then what we need is not the value 2, we need to know this value, right? We need to know the mu value that we actually shifted up. So the ultimate goal is to solve for mu. So I come back to my original function, f sub mu of y, which is y squared minus 4y plus mu, has to be equal to 0, and put in a 2 for y. So 2 squared minus 4 times 2 plus mu has to be 0, and you end up with negative 4 plus mu is 0, so mu is 4. So that's your general process for finding the bifurcation value. Take the derivative, set it equal to 0, solve for y, plug that y into f sub mu, solve for mu. Maybe I should write down those 2 steps. Hang on one second. I'll answer that in a minute. Set f mu prime of y equal to 0. Solve for y. 2. Plug result from 1. Into f sub mu of y equals 0. Solve for mu. Okay, so the question was, why is y suddenly the independent variable? Okay, because y squared minus 4y plus mu was representing the right-hand side of the differential equation. So we just said, let's examine what happens to the right-hand side of the differential equation as we change mu, right? So we let this is y, and this is y squared minus 4y plus mu. So it's just a name of the variable. Could have easily have called it x. All right, so we found the mu value. Mu is 4. We have a general way to find the mu value. So next thing we do is we choose 2 nice numbers, one a bit larger than b, right? We're calling b for bifurcation value. It happens at 4. Okay. So I want to choose 2 nice numbers, one a little bit bigger and one a little bit smaller than b. Okay, so somebody give me a number a little bit bigger than 4. 5, I like it. How about a number a little bit smaller than 4? 3. Okay. So on the same axes that we've been drawing the parabolas, where we have f sub 0 and f sub 4, I want to put in f sub 5 and f sub 3. And I'm going to be careful to make sure I do the x-intercepts accurately. So f sub 5 is y squared minus 4y plus 5. Okay. And could we find the horizontal intercepts of that function? How? Quadratic formula. Yeah, I don't think it factors, but I could use a quadratic formula. And f sub 3 is y squared minus 4y plus 3. That one actually factors negative 3, negative 1. Yeah. So 3 and 1 would be the x-intercepts for this guy. Okay. That one I need the quadratic formula. I can't remember what they are off the top of my head. All right, so I'm going back to my parabola graphing. This green one was f sub 4. All right, and then I'm going to do f sub 5, which means go up to here. And it actually has no x-intercepts, right? Because it's going to open up, so I don't have to be careful about that one. That's f sub 5. And then finally, oh, it is. You're right. I didn't look at the scale. There we go. Okay, and then to do f sub 3, I have to go down 3 from go up 3 from f0. So that would be like right here. And it has x-intercepts at 1 and 3. All right, so we've got 4 parabolas graphed. The f sub 0 was our original. And then we have the bifurcation point, the place where this parabola goes from having 2 x-intercepts to 1 to none, right? As you shift this parabola up and down, the place where things fundamentally change is f4, right? Anywhere before that, we had 2 x-intercepts, which is 2 equilibrium solutions to the differential equation. At 4, we have 1. It goes from 2 to 1, and after 4, we go to 0. No x-intercepts. So the bifurcation, the fundamental change happens at 4. Mu equals 4. All right, so there's our parabolas. All right, drawing the bifurcation diagram. So first you draw a set of axes, and we're going to label y the vertical axis, and mu is going to be the horizontal axis. So for each value of mu, I'm going to draw a phase line on this set of axes. So I'm going to draw vertical lines at 3, 4, and 5. Right? Those were our choices for B minus and B plus. And then we're going to use the parabolas that we graphed to draw in the arrows and the dots that will make those vertical lines into phase lines. So I want a vertical line at 3 and at 4 and at 5. 3 and 4 and 5. Okay. So let's think about 3. For mu equals 3, that's this guy. And where are the equilibrium solutions? 1 and 3. So I put the dots at 1 and 3. Okay. And when I'm less than 1, is the parabola positive or negative? Positive of the x-axis. So I've got an up arrow. Between 1 and 3 goes down below the x-axis. It's negative, and then it's positive again. All right, so for mu equals 4, what's my equilibrium point? 2. Okay. And before 2 and after 2, positive. The whole parabola is above the x-axis except for this one little spot that sits on the x-axis. So this is all positive. And then at 5, equilibrium solutions? None. So I don't put any points on the vertical line. The parabola is always above the x-axis, so I can put an up arrow for the solution is going to be always increasing. All right, so these are phase lines. All right, so then let's add the phase line that we drew for f sub 0, right, for when mu equaled 0. So that would be here when mu equals 0. What were my equilibrium solutions for that one? 0 and 4. And it was positive, negative, positive. That's the phase line that we drew right next to f sub 0. Okay. These are the only, ignoring f sub 0, these three lines that we drew here, those are the only three qualitatively different phase lines we're ever going to draw, right? It's always going to be either two equilibrium points, positive, negative, positive. This is the only one equilibrium point, and then the rest will have none, right? So if I draw in some more vertical lines, like between the ones that already exist, I don't have to calculate exactly, but I know that anything before 3 is going to have two equilibrium solutions, and they're going to get further and further apart as the parabola moves down, and it's going to go positive, negative, positive. And then until I hit 4, I'm going to have two equilibrium solutions, right? 4 is the first place as I move that parabola up that it's going to have just a single x-intercept. So I'm going to have two here. They'll be a little closer together as I get closer to 4. And it's going to go positive, negative, positive. After 4, I have no equilibrium solutions. As soon as my mu value gets bigger than 4, my parabola is now sitting entirely above the x-axis, and no equilibrium solutions, just positive arrows. So as you start to draw it, you can see a shape take form with the equilibrium points. And you can kind of trace it out with a smooth curve best you can. And this thing is called a bifurcation diagram. It shows you all the qualitatively different solutions in one picture. All the different types of phase lines you could have in one picture. Pause, people are still right. Okay, so now I'm going to draw 3 different sets of qualitative solutions. So a phase line is a way of putting all the information about a solution in one like little compact picture. But I'm actually going to draw solutions now to each of these differential equations, and these are just t, y axes, right? Just the independent variable, dependent variable. So I'm using b minus, that was 3, b is 4, and b positive, b plus is 5. Okay, so for mu equal to 3, we had equilibrium solutions at 1 and 3. 1 and 3, can't remember. Let's go back to our bifurcation diagram. For mu equals 3, equilibrium solutions at 1 and 3. Yep, here and here. So I draw in my equilibrium solutions at 1 and at 3. And then I can sketch solutions for various initial values. You should always pick an initial value on either side and between any equilibrium solutions. So if I were going to draw a solution that has initial value, say 0, 0. As t goes to the right, what happens to the value of y according to our phase diagram, our phase line? Yeah, because I'm starting less than 1, and this arrow says that my function increases. It's gonna go towards the equilibrium point. Okay. From either side, my solutions go towards 3. 3 is a sink, so that means that whether I start below, sorry, 1 is a sink. So whether I start below 1 or above 1, my solutions are going to approach 1 because it's a sink. All right. What about in the other direction? What happens as I go away from 1? Yeah, my function has to always be increasing. This arrow indicates that the function's increasing, right? So it has to be increasing forever, right? So it's increasing towards 3, and it has to have always been increasing. So it has to be draw it as an always increasing function. All right, and what about between 1 and 3? It was a down arrow, right? Which means the function has to be always decreasing. So you have to draw it so that it's always decreasing. And then if I had an initial value at 4 above 3, what does my arrow look like above the equilibrium point of 3? It points up, so my function is going to be increasing. So I would draw it like this, something like that. And you can never cross the equilibrium solutions. So I have 3 possible qualitatively different solutions depending on my initial value. Any other initial value will look something like one of these 3. Like if I picked this guy, it would look just like the one above it. I just picked a random initial value that was bigger than the 3 equilibrium solution. So these 3 points, this one, and this one, randomly chosen, one below the equilibrium solution, one between the 2 equilibrium solutions, and one above the other equilibrium solution. Yeah. Yeah. I just followed the directions, right? It says include all equilibrium solutions. So I graphed those first, right? And then also at least one graph in any region above, below, or between the equilibrium solutions. Yep. Yep. Yeah, and that's exactly what I was just about to do. If I had picked 0, 5, it would look just like the one I drew at 0, 4. It would just be up a little bit. Qualitatively, they'd be the same. If I had picked this point, right, it would look like this. Okay, so for mu equals 4, there was only one equilibrium solution. Okay, so these solutions are going to be qualitatively different than these ones. So I'm going to draw my equilibrium solution. It was at 2. Okay, so that's one solution. And then pick any random initial value above and below that equilibrium solution. So let's say I pick 0, 0. Okay. When I'm below 2 on the phase line, for mu equals 4, my arrow is pointing up, right? In fact, the arrow on this phase line, the arrows on this phase line are always pointing up. So whatever function I draw is always going to be increasing. So this one would be increasing towards my equilibrium solution. And if I picked this guy, it would increase like that. Because it's an always increasing function. That is a node, yes. That equilibrium solution is a node. And then for mu equals 5, there are no equilibrium solutions, right? So there's only one region. So I'm only going to draw one. Maybe I'll pick 0, 0 as my equilibrium point. The only piece of information on the phase line at mu equals 5 is an arrow pointing up, which means that the function has to be always increasing. So qualitatively, it does something like that. There might be some waviness, right? That's the long run behavior. Sure, yeah, you could draw it linear. Yeah, these are strictly qualitative in that they're showing sort of the general long run behavior of what the functions do. This one goes up to infinity and down to negative infinity. Okay, so I'm giving you one to try on your own. and follow the same kinds of ideas. Let me know if you have questions.